All right, it's 11 o'clock. So I want to go fast here because there's two things I want to do before we start doing the review. Finals on Tuesday, 11 to 1:45, right? Obviously, we don't have class on Thursday, right? So that's it. We just meet next week. We're done. On this final, you can bring all your formula sheets, right? Everything that is online for you, right? Yes? Okay. Any questions on that?
I'm literally bringing everything.
Yeah, bring it. Bring it. Okay, then let's get down to what I want to talk about today. So first thing I want to do, remember we left off with that beautiful equation thing? I'm going to get to that. I want to do something else first. So let's say we were asked to do this integral. Let's do, how about sine x over e to the x dx? Now we have different ways to do this actually. We can do this with integration by parts, but I want to show you something else, another way to do it with power series. So what I can do is try and rewrite this as a power series instead, using the Maclaurin series, which I have on the board over there, which you have on your formula sheets. So I'll come back to this. Let me write down what sine x over e to the x is. Sine x, the power series, right, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. One more, x to the 9th over 9 factorial plus dot, 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 right? That's sine x. And what I'm doing is I'm dividing that, right, by e to the x. And e to the x is 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial plus dot, dot, dot forever, right? That's what that means, yes? So I can actually simplify this and make this look a little better by doing division, by actually dividing these two things. But to do that, I'm going to have to use something called long division, which is something we learned back in college algebra, right? So when you're trying to divide something, I'll remind you, if you're trying to divide something like x squared plus x plus 1, let's say you want to divide that by x minus 4, we would do this. Like this, and outside here we would do that. Then we'd try and figure out what we multiply that by to get this. That look familiar? Long division? I'm going to do the same exact thing, but with this. So it's going to look horrible, but it's the same procedure. All right? So inside the division box goes the numerator. Watch the way I do this. X plus nothing minus x cubed over, actually, you know what? Let me do it this way. 0 plus x plus 0 minus x cubed over 3 factorial plus 0 plus x to the 4th, x to the 5th, sorry, over 5 factorial plus 0, I'll do one more, plus x to the 7th over 7 factorial plus dot, 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 right? So I put zeros in there, right?
Yeah, the minus x to the 7th.
Oh, minus, yes, thank you. Right, I put zeros in here, right? And that's because with long division, we want to account for every power of x in our division box. That way, if anything, when we do the multiplication here, if anything needs to line up under, let's say, x to the 4th, I have a position for it, all right? That's the numerator rewritten. Now, outside goes the denominator. So I put that 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus dot, 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 right? Now we start to do the long division. And the way long division works is you look at the first term here, And then over here, you look at the first non-zero term, x, and you ask yourself, what do you multiply 1 by to get x? X. So that goes here. And now what you do is you actually multiply each of those terms by x, right? So I do x times 1 is x. I put it under here. X times x is x squared. Where do I put it? Right here, right? X squared. It'll be plus, right? Because it's positive. And then x times x squared over 2 factorial is positive x cubed over 2 factorial. So that's this x times that. So it just adds another power of x, right? And then x times that will be x to the 4th over 3 factorial. And I put that under here. Y'all see what I'm doing? Yes? Any questions? And I could keep going, right? I could keep going? Okay.
What did you start under the x?
Why did I start under? Well, what's x times 1? I don't know if this is what you're asking me. X, right? So I lined it up with the x terms. This would be, wait, right here? Because that's for any constants I have. Like if I had a constant, I would put it here. So look at it. Each one of these columns is like x powers going up. So this is like no x's, right? X to the 1st, x squared, x cubed, x to the 4th, x to the 5th, x, so on and so forth. Was there? I thought I saw another question. No? Yes?
Is it the factorial 3 factorial or is it 4 factorial?
Where?
For under the x to the 4th.
Where? Oh, yes. Here to here. Thank you. 3 factorial. Yeah, because all we're doing is this times this. Thank you. I said 3, wrote 4? Yeah, probably. I checked out like 8 weeks ago. No, I'm kidding. All right, so now what do? Once you have this, you flip the signs. So you change the signs of everything. So I change this to a minus, change that to a minus, change that to a minus, change that to a minus, and I keep going, right? All right, add down. So the x's go away, and then here what do I get? Minus x squared. Okay, this is going to be a crappy one. This one right here.
Is that negative 2x cubed over 2 factorial?
Where? This right here? It's a negative x cubed over 2 factorial.
No, but I was going to say, is that negative 2 when you combine them?
Oh, well, yeah, I'm going to do that over here. So, well, I'm going to do it over here. So what I'm doing is I'm taking negative x cubed over 3 factorial. What's 3 factorial? 6. I'm subtracting from that because I'm adding a negative, right? X to the 3rd power over 2 factorial, which is 4. And to put those together, I have to get a common denominator. What?
2 factorial.
Shit, man, what the hell? I'm so done. Okay, I'm so done. So this plus this are subtract, right? So common denominator, multiply top here by 3, bottom by 3, you turn into a 6. So you get negative 4x cubed over 6, which is negative 2x cubed over 3. Right? Just, is that all right with y'all? That goes here. Negative 2x cubed over 3. And then I have this one. Well, fortunately for me, there's a 0 here, right? So that's going to be minus x to the 4th. Let's go ahead and just turn that into 6 down there. 3 factorial. Yes? Yes. Okay, now we get to play that game again. We say, all right, what do I multiply this by to get this? Minus x squared, right? So I put that here, minus x squared. And then I go and do it again. Right? What?
Okay, so I thought, I don't know why I thought we were going to like ask that same question but with the x term as we started the first time.
No, you always work off whatever comes out on this next line. That's what you work off of. And you're trying to turn that first term over there into this now.
Okay, gotcha.
So I put minus x squared. And now I distribute again. This times 1 gives me negative x squared. Put it underneath. And then the next one, this times this is negative x cubed, right? That's it. So that goes underneath here. So minus x cubed. And then we'll do one more. This times this one, negative x to the 4th over 2 factorial, which is 18, right?
Yes, Because it is.
Thank you. 2 factorial is 2, right? And I could keep going, couldn't I? I keep going. I'm not going to stop there because this keeps going, this keeps going. But now I'm going to come through and I'm going to do the same thing. I'm going to change the signs. So now this becomes a plus, plus, plus. And let me add down. These go away, right? These two together, x cubed over 3. X cubed over 3. And then these two, I don't care, okay? The idea is, I think you're getting the idea of what I'm doing here, right? So now what I would do, next line is whatever, and now I again turn the 1 into this, right? Yeah. So I have to put up here x cubed over 3, and then I just keep playing this game, right? And I could theoretically play this game forever, couldn't I? Yes. And so if I play this game forever, I'm going to get up here a new series. Do you see? This is a new series. And that is what you could integrate. You integrate this series. And that would be your antiderivative in its series form. Y'all follow that?
So you get the same answer as
you get the same answer as you would had you, well, we're doing a series, right? So it would be an approximation in some sense. But if we can do this for any function here, we can do it series. So it's more powerful than the methods we have. You know, everything we've developed, and I probably said this to you all before, all the methods that why is the, oh, I don't normally have this here. I'm like, why is that? This looks different. All the methods we've developed in this class, in the real world, most of the time, if you're given like you find a function in the real world, that function is not something you can integrate easily. This is not going to cooperate with me. I don't know why my laptop does this. Sometimes when I open it, it just fires right up. Other times, it's like in some weird sleep mode that I can't.
So how many terms do you want to talk?
Well, if I asked you to do a problem like this, right, I would tell you how many. I would say, find the first 3 terms of this written as a power series. And so you'd be done at this point.
Well, you still have to integrate it.
Well, then you have to integrate, right? That's not going to come on, so we're not going to look at it. But I was going to go to Wolfram, and I was going to type in sine x over e to the x. And then Wolfram would have probably given me this series. It's something like you scroll down, it would say series, and it would actually have this.
Can you just do it with the ends without breaking all down?
Can you do no, because the division won't work that way. Are you saying use the summation formula, the sigma notation? You can't do anything with it. Because if you have this notation for sine, right, it was -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. That's sine. And then you divide that by this sigma notation, right, which is the notation for e to the x is x to the n over n factorial. Like, how do you divide that? You can't just do this divided by that and do the reciprocal. It doesn't work that way because this is a sum, right?
Right.
So the only way you can do flipping is if it's something, you know, like if I had 4 plus 1 over 3 plus 5, I can't just flip, right? I can't just flip. Like even if this was let me do it a different way. Let me just do this. 1/2 plus 1/3 over 1/4 plus 1/8. I can't just like flip this up, right? Remember, this goes forever. I'd have to combine them, but it goes forever, so you can't combine them. Yeah. Okay, so that's just to show you, right, this. So to come back over here and answer the question, this would be the integral. If I just have the first 3 terms, the integral of x minus, let me write it this way. X squared. And then I'm going to write plus 1/3 x cubed plus dot, 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 right, dx. A lot of times you can look at this and come up with a formula for it and put it into sigma notation. But I'm just going to leave it like that. Then this equals, now we do the antiderivative. I know I'm going to have a constant because I'm doing an antiderivative, and then I just integrate each one. antiderivative of each one of these terms. And now, if you give me like limits of integration, if you want me to go from like 0 to 1, then I just plug 0 and 1 in there, subtract, whatever, and I've got an approximate answer, and I can get as close as I ever need to be, right? All right, so that was the first thing I wanted to show you. And then the second thing was that formula. The e to the, unless y'all don't want to see it, we can just start reviewing. It's totally up to you guys. Should we vote? Do y'all want to see this or not? Yeah? Okay, let's see it then. All right, so what we established last class, or I talked to you about, people argue that's the most beautiful formula. We started talking about imaginary numbers a little bit, right? So before I can do this and prove this to you, a couple of quick little ancillary things. Do you agree that all I need to do is this? Oops. If I can show this, want to show. All I want to show is prove to you that this is -1.
Yeah.
Do you all believe that? If I can prove to you that that's -1, if that's -1 plus 1, it's 0, it's true, right? Or just move this 1 to the other side and that's this, right? So I'm trying to prove that to you, right? Next thing I need to show you, or that we need to get in place, is that when we talk about I, the imaginary unit here, I by definition is the square root of -1, right? That's the definition of I. And I want you to notice that if you take I and you square it, you get what's underneath the root, so you get -1. So I squared is -1 by definition. And then if I cube I, what happens? So you get, the way I like to look at it is this. It's actually I squared times I. Isn't that what I cubed is?
Yeah.
And what was I squared?
-1.
-1. So what's -1 times I? -1 times root 1. I'm just going to write -I. How about that? Just -I. So I cubed is -I. What's I to the 4th? It'll be, I want you to look at it this way. I squared times I squared. Do you all agree that's? Yes? So that's -1 times -1. That's 1. Y'all buying this? What's I to the 5th?
It's the first one again, isn't it?
You could say it's I to the 4th times I, right? That's I to the 5th. And I to the 4th was 1, and 1 times I, that's just I again, right? And then what's going to start happening? It's going to start repeating itself, right? So the I has what we call a cyclic nature. It cycles, right? And so I'm going to put that over here. So if we have I to the first power, I to the 5th power, well, I'll do it this way. I equals I to the 5th power. What would be the next one that would get back to I? I to what power? 9th power, right? So we would go 5, 6, 7, 8, and then we come back up and be at 9, 10, 11, 12, and then, right, 13, and then back up. Yes? So I to the 9th would be the same, and then I to the what? 13th, and then so on and so forth, right? You see the pattern? I is the same as I to the 5th, I to the 9th, I to the 13th. And then I squared is the same as I to what power? 6th power, and then I to the 10th, and so on and so forth. I'm just adding 4 to each time I do this, right? And what is that, though? What was I squared? -1? And then I cubed, what was I cubed? -I. So I to the 3rd power, I to the, add 4, 7th, I to the 11th. All of those would be equal to what? -I. One more. I to the 4th would be the same as I to the 8th, which would be I to the 12th, right? Which is all equal to 1. Okay. I need all that. Ready to do it? Okay, let's do it. Remember, this is what I want to show you, right? I want to show you that this is true.
As a real quick note, so like my first instinct would be to take the natural log, but I don't know how that would work, because you can't take the natural log of -1.
This is not an equation you're allowed to work with.
Oh.
We're trying to show this is true, right? so if you're trying to show something's true, you have to start on one side and turn it into the other side.
Oh, like a proof.
It's a proof, right? So I'm going to try and prove to you that that's true. So the way I'm going to do this is I'm going to do the following. I'm going to say, what is e to the I times x? Now, what I'm doing here is I'm saying, look, we have a Maclaurin series for e to a power, right? This power up top, that x, can be anything we want. And the way you use the formula is you just plug into that series, right? Man, that marker's greasy. Right? You just plug into that formula, whatever's in that green box, right? That's in our box here. That's the x in the power series. So let's write out the Maclaurin series for this, replacing all the x's here with ix. So what would we have? 1 plus ix plus ix, that quantity squared over 2 factorial, ix cubed over 3 factorial. I have to go quite a ways here. Ix to the 4th over 4 factorial, ix to the 5th over 5 factorial, ix to the 6th over 6 factorial. I'm going to go maybe 2 more. Ix to the 7th over 7 factorial, ix to the 8th over 8 factorial, right? Plus dot, dot, dot. That's what that is? Everyone buy that? Okay, but this is just, let's see, 1 plus ix plus, okay, now when you do this, what happens when you square, because these are multiplied, what happens when you square I? What's I squared? Negative 1. So this actually turns into a minus, doesn't it? Yeah. That I squared becomes a minus, and then the x just gets squared, and you have over 2 factorial, right?
Okay.
Yeah. This one, what's I cubed? Negative I. So I'm going to write negative I out front, and then x cubed over 3 factorial. You following what I'm doing there?
A little off, but like, so is this the only scenario that you can square something and get negative?
Well, if you're using I, yes.
Yeah.
I mean, that's the whole thing about I.
Kind of weird.
Yeah. All right, next one. What's I to the 4th power? 1. Okay, so this is just going to be stay plus x to the 4th over 4 factorial, right? Okay, now we're back to the same pattern, right? So I to the 5th was what?
Was it negative 1?
What's I to the 5th?
Oh, it's the first one, so it's...
Just I, right? So I'm going to say plus, I have an I here, then I have the x to the 5th that was up there with it, and then 5 factorial, right? I to the 6th, negative 1, that's going to make it minus, right? And then x to the 6th over 6 factorial. I to the 7th, negative I, so I put minus I out front, and then x to the 7th over 7 factorial. I to the 8th, just 1, so I'm back to this, x to the 8th over 8 factorial. Got it? Plus dot, dot, dot. All right, now what I'm going to do is rewrite this. Watch, I'm going to say 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. What I'm doing right now is I'm writing all of the terms that don't have I in them together. Right? Those are all the terms that don't have I. This, that doesn't have an I, 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 and there's an infinite number of them, right? So this keeps going, doesn't it? Bless you, plus dot, 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 dot.
Is that the cosine?
Hold on, yeah. I mean, yes? So y'all see that? Then I'm going to start writing everything that has I in it. So this is Ix, right? And then minus I times x cubed over 3 factorial. Some of y'all are seeing it. Plus I times x to the 5th over 5 factorial. Minus I times x to the 7th over 7 factorial. And then it would keep going, wouldn't it? Yes? All of these have an I in them, don't they? So I can factor an I out. These I'm just going to leave. So plus I factored out of these would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, 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 dot forever, right? So it's this plus I times that. And this right here is cosine x plus I times sine x. And so what we're saying is that e to the ix, right? That's what this was. E to the ix is equal to that. That's a famous theorem from pre-cal. In pre-cal, sometimes you get to that, sometimes you don't. But you see that in pre-cal, but in a slightly different manner. You usually don't see this part of it. You just see that part. Okay, that's what e to the ix is. Now, what are we trying to figure out? What am I trying to show you? What's e to the I? Pi, right? So now plug in pi in for this, for x. So e to the I pi will be equal to cosine pi plus I times sine of pi. Sine of pi is 0. And cosine of pi is -1. There you go. So it's done. Pretty cool, huh? So there's actually a more general formula for this. This is, I talked to y'all last class because y'all asked about it, like that we don't study complex numbers, right, until you get past the calculus sequence, right? We did mention that at the end. So in a class called complex variables, what you learn is that every number in the complex plane, because I told you you need 2 dimensions, right, to draw a complex number. So if you take a number in the complex plane, like this, it has some a and b. And so we could call that number a plus I times b. That's the way, or b times I. We'll do it that way, bi. That's that number, whatever it is. So if I write 3 plus 2i, that means you go over to the right 2, you go up, sorry, to the right 3, you go up 2. That would be the complex number 3 plus 2i. There's another way you can write that number. You can write that number this way. Let me do a different example. Let me go 3, 4i. So that means I would go to the right 3 and go up 4. That complex number can be written this way, or you can write it this way. That distance, what is that distance? Y'all know distance from here to here? I made it a 3, 4 triangle. Do y'all see 3, 4? Yeah. So that has to be 5, right? Yep. And then this angle, theta, right? Whatever that theta is, you could find that theta on your calculator because you have all the sides, so you could do like inverse tangent or something on your calculator. You can rewrite that angle. You could rewrite this number in a different format. Here's the format that you could use. R e to the I theta. So let me just explain quickly what I mean. R is this radius, distance from here to here, and theta is this angle. Okay, so every complex number can be written, either give me kind of like its x coordinate and y coordinate, even though it's not x and y, it's the real part and imaginary part, or I can give you the angle and how far to walk out. Okay? So if you look back at this, right here, e to the I theta, knowing that now, what's the r in front? 1, okay? So I'm saying you're going to walk out 1 and you're going to turn by an angle of what? Pi. So walk out 1 but turn by an angle of pi. Pi's over there, right? Walk out 1, where are you? -1. You see? Now look at this. This number right here, straight up 1 right there, that complex number is the number 0 because you don't go left or right and you go up 1. So that's just 1i. Do y'all see that that's that complex number? Well, that's just I, isn't it? That's just I. Okay, so how could I rewrite that using this form? e to the I, right? So it's out, you walk out 1, and then your angle is pi over 2, right? Another way you could write I is e to the I times pi over 2. Now, what's cool about doing it this way is that if you ever take a complex number and you square it, right? If you want to square that number, what you do is you you square the r and you double the angle. So give me any complex number. If you square it, square the distance and double the angle. So if I ask you to square I, what's I squared, right? If I ask you to do what's I squared, you're going to square this, right? Okay, so if you square that, you're going to square the radius. So how far are you going to walk out? 1, you're going to double the angle. What's twice that? Pi. So you're going to go to e to the I pi. But where's e to the I pi? -1, which is why I squared is -1. Anyways, it's crazy. It's awesome. Complex numbers, just like this different universe. So if you ever get a chance to take that class, it's fun.
Are the equations still valid? Like, in other words, you have e to the I pi, I think you said something about that earlier, but is I pi equal to the natural log of -1?
Is what? Is
I pi equals the natural log of -1? Even though the natural log of -1 is normally not.
Oh, you're saying, okay, so you're saying, can I come in here now and do natural log of both sides? Well, that's not going to be defined, right? So your natural log function is restricted to the reals. The question would be, can you extend it into the complex? There's ways to extend it in, yeah.
So like, I thought the whole thing with the imaginary numbers and complex numbers was that you knew that a point existed like in a general area, but it seems like what you mentioned with the inverse tangent and all that, like wouldn't that give you an exact number?
Would what give me an exact number? Inverse tangent?
Like you were saying, you could take the inverse tangent of a complex and you could effectively get an output. But wouldn't that imply that like you could pinpoint where that would be exactly? Like if it's like,
I'm not following you.
I don't know.
Yeah.
I think I get what you're saying. If I understand what you're saying, right, every number can also be translated into something like a complex number.
Every real number you've ever learned is a complex number, right? Because all it is, the complex plane is actually your real number axis, the real number line you've dealt with your whole life actually lives here, okay? But you have this additional dimension, which is called our imaginary axis, which adds this up and down adds the I into it. So if you're somewhere here, like that point right there, right? That's, let's just say the number 2. That's the same as 2 plus 0i,
Yes, yeah.
okay? So let's write it, let's use that form r e to the I theta. So how far do you walk out? 2, okay. 2e to the I, what's theta? 0. And what's I times 0? 0. What's e to the 0?